Today we are going to design a full adder using FPGA VRSI implementation. So in this, what is the full adder? Full adder consists of a 3 bits input A, B, and C in and gives output as a sum and carry. Okay, but in this we are not only going to implement the full adder in the simpler way by AND gate, OR gate, XOR gate, but we are going to implement by using two half adders. So how we will implement? The first two inputs are given as A and B, and we are doing the XORing of A and B. Okay, then output of this is given to the XOR gate with the C in, which is the input of the previous state. Okay, then we get the sum as C in XOR A XOR B. Okay, and then in the next step, when we are going to take inputs as A and B, then we will do ANDing of A and B. This output will be given to the XOR. Then again we will take the A XOR B output and C in as an input, and then we will again do the ANDing of this, in which there is an ANDing between the C in and A XOR B, and then we will get a output, and then this is connected to the OR gate, which we will get the C out. Okay, so this is the full adder. Now we will implement in the Vivado software. So now we will create a new software, full adder, and next, I will take it as a full adder 1. Next, then we will select the board. Next, finish. Okay, so your new project is created. You can see in the updating, now you can see in the design sources. Now we have to add the sources. So in this, we will make a create the design, but we have to add files for the half adder. So we will add a half adder VHDL file in full adder file. Then you can see half adder VHDL file libraries and where the location of the half adder file is. So we added the half adder VHDL file. Then finish. Okay, so now you will see here half adder file. Now we need to create the source file for the full adder also. So we will create a file. Select VHDL, select full adder. Okay, finish. Then we need to set our input and output. Okay, so I will take here as A, then I will take here as a B, then I will take here as a C in to differentiate, then I will take here as a S sum, and I will take here as a C out. Okay, these two are the outputs. The architecture name here selected is behavioral. Okay, then we do OK. So now in this the two files are opened. So we will now write a code for the full adder program. Now the code is been written and you can see that no errors are here in this code. So I will now explain the code in which the starting two lines are the library files used over here. Then full adder, here the entities of the full adders are being shown. The A, B and C in are the input for the full adder and the sum and C out are the output for the full adder. Okay, so after this the architecture structural of the full adder. Now here we have to also declare the half adder components in this code. Okay, so we have to declare. So in the previous video I have shown that how the half adder is implemented on the Vivado software. So this A and B are the inputs, S and C are the outputs. What is S and C? S and C is the sum and carry. Okay, so this block is ended by the end component. Okay, after all, what is this internal signals and wiring? So these internal signals are used to help the connect one block to the another. Okay, so this one S1 is the sum from the first half adder. C1 is the carry from the first half adder. And C2 is the carry from the second half adder. Okay, now we will write this code for these three conditions. So for half adder 1, the first half adder adds A and B. Okay, so we port map this to A, B, S1 and C1. Then in the second half adder, it adds S1 and C1. Okay, so S1 and C1. So in the what is the inputs in the first half adder? That is the A plus B. In the second half adder, it is S1 plus C1. Okay, so we port A to S1, B to C in, S to sum, C to C2. Okay, so you can compare here, like here what we have did A plus B. Here what we are doing S1 plus C in. So A is mapped to S1 and B is mapped to C in because our A and B are the inputs. Okay, here S1 was your output and C1 was a carry. Here sum is your output and C2 is your carry. Okay, and then in the third step, which is a carry output logic, there is a ORing between C1 and C2. Okay, so where do we get the C1? C1 we got from the A plus B and C2 we got from the S1 plus C. So here we end the structural. Okay, carry will occur only if the first HA generates carry or second HA generates carry. Okay, so this we got. So now we will run the stimulation. No, we will make the synthesis. Then okay. So I will open now the synthesized design. After this, we will check the schematic over here. See now, you can get A, B, C in as your input and sum and C out as your output. Okay, so we got the appropriate schematic. Then now we will write the test benches for this code. Okay, so as we are done till here, we will close this synthesized design. Okay, and we will now create a test benches for the full adder. So we will go for the adder create stimulation sources. Then we will move to the next. So we will create a file VHDL. File name must be same. So full adder. Okay, you have to press OK. Okay, this. Then you have to finish. Then behavioral same as it is and okay. So yes, so this is the simulation file created. Now we will write the test cases for this file. So now after creating the simulation file for the test benches, so why test benches are used? Test benches are used to clarify or verify our circuit that after changing the input, does output changes correctly or not. So in this, the first two lines are for the library, for the STD input and output. Then this is the entity of full adder TB and entity of, and this is the end of the full adder TB. Okay. So this test bench has no inputs and outputs. It is only used for the simulation purpose. Okay, then there comes the architecture behavioral. It contains component, signal, and stimulus. So first is the component. It declares the full adder design and matches the exact port names of full adder. Okay, so this is a full adder design. So say C, A, B, C in these are your inputs and sum and C out are your outputs. So this is the end component. So second comes the signals. So signals means three inputs are given to the A, B and C in. So initially we give as a 0, 0, 0 and C out and sum are used for the observation, okay, in the waveform. So now we will begin our code which initiates our code. Then DUT is a device under test. It connects the test bench signals to the full adder ports. Okay, so what it connects the test bench signals, the signals which we will pass through the test bench with the full adder ports. Okay, so port map, they will map the port A to A, B to B, C to C, and sum to sum count. Okay, then stimulus process. Okay, uh, okay, so now we will move to the stimulus process. In the stimulus process, it generates the all possible input combinations of the A, B, and C. Okay, so we can like verify how we used to make a truth table. So these are the 4041s, 2021s, 2021s, and 0101. So the truth table we make for the full adder has been created in the test benches. Okay, then wait, which is used for the which is used to uh, come out of the loop, otherwise it will go to the infinite process, and this is the end process, end behavior. Okay, so this file is now saved. So after saving this file, we go in the run simulation. We here click the run behavioral simulation. Okay, so we will wait until the execution will take place. So you can see over here. Okay, so you can see over here that how the waveforms are created. I will zoom it a little bit. You can see how your waveforms are created. Okay, so for the sum and C out, see how the waveforms are created in the sum and C out. So okay, so you all got the your waveform, and we also changed the input and we got the output as per the full adder working. Okay, so this is the timing diagrams, and we can also change input and output from here. Okay, so now we need to create a bitstream file. So we will create a run implementation. Then after the run implementation, you can see over here that it is processing, and we will wait until it processes. So implementation is successfully completed. So now we will generate a bitstream file for the, we have to upload the code into the bitstream file. So we will create it. Okay. The bitstream file is actually used to upload on the FPGA board, but eventually we don't have the FPGA board, which is the mostly used as a basis or basis 3, which is of Atrix. So we don't have, but you can learn up to here. There are more further hardware connections which are need to be done in the basis 3 code. but due to unavailability of the board, we will. So here we got the bitstream error. So how to handle the bitstream error today I will teach you this. So in the whole process we forgot to create a constraint file. So we will stop the simulation. Why this constraint file is used? Because constraint file consists of the constraint which is used to connect the FPGA with your stimulation. So we will create a constraint file, finish. Okay, so we will check what have we written over here. So we didn't write any constraint. So I will just explain this, that this is the input property in which the port A is connected to V17 of the FPGA board, and this is the input standard VCMOS33, in which the voltage given to this line must be 3.3 volt to the port A, and similarly for input and for the carry, then output and for the sum and C out. Okay, so we will save here. So then we will go to the run implementation. We will go yes. Okay. So after this implementation is completed, we will go for the generate bitstream. Okay, so now we resolve the problem. That the problem was in the constraint file. You have to map the ports of your total code with the FPGA in which you will install. So don't forget to create a constraint file. So now we will open the hardware manager, and the hardware manager file is open. So later you have to select the target and all and add this code into upload this code into the FPGA port or a board. So this is for today, which we implemented the full adder in the FPGA using VLSI techniques.